Hello, everyone. Welcome to a new series of lectures on portfolio management. When it comes to portfolio management, it's a very hot topic, right, for quant practitioners. Um, I'll take you through the entire journey of how this whole thing started, starting with Harry Markovich, and then William Sharp, and then Black Litterman, and then all the modern developments in this particular field. So, yeah, today's topic is modern portfolio theory, also known as MPT. Okay, so let's get going. All right, here I have the picture of Mr. Hari Markovich. Um, so, when it comes to portfolio management, before Harry Markovich era, right, people only cared about expected return. Okay, so the idea of portfolio selection in terms of what assets to include in your portfolio was primarily based on which assets are having high, more expected return. Okay, so that was the single most important attribute for portfolio selection. People knew this idea that do not put all your eggs in one basket. Okay, this is a popular saying that existed before Harry Markovich. However, there was no quantification of risk. All right, the notion of risk was there, but there was no way to quantify that risk. So Harry Markovich was the first person who actually quantified or formalized the notion of risk by stating that risk can be measured by variance or standard deviation. You can use them interchangeably, it's fine. So that was the first serious thought process in terms of quantifying risk. Now, the moment you quantify things in in finance, right? We don't have shortage of techniques to do further treatment. The biggest challenge in finance is to quantify things. Okay, utility function, risk, all kinds of intangible things, right? So once you have quantified risk as standard deviation or variance, then the floodgates of quantitative techniques opened up. All right. So that was the contribution. And then, so Harry Markovich came up with this paper in his PhD thesis called as Portfolio Selection back in 1952. So there is a nice video on YouTube that where he shares his experience. He knew that he's going to get his PhD, obviously, but he didn't know that later on he will be awarded the Nobel Prize for this one. And yeah, it's very interesting. Take a look at the video on YouTube. So there are several things that came out of his paper. I actually have the paper. It's freely available online. If you want, you can. Let me quickly show you. Just Google portfolio selection. This is the paper. It came in 1952 by Harry Markovich. Portfolio selection. That was his PhD thesis. Okay. So yeah, he also showed that you can reduce risk by diversification. Now, this idea is similar to this particular saying, do not put all your eggs in one basket. You're supposed to diversify. Put your eggs in different baskets, not everything in one basket. And then based on, the idea of thinking of risk as variance, other things opened up. For example, we could also quantify diversification through one parameter called as correlation. Okay, correlation or correlation matrix. So we'll see all those equations later on. But yeah, that was his biggest contribution. And then after this particular theory came out, there were a lot of subsequent developments. So Harry Markovich's protege, William Sharp, he came up with the idea of, you must know, right, CAPM model, capital asset pricing model. That is something we'll discuss later on. It is an equilibrium model that basically gives a relationship between the asset return versus the market return. Market return being one single risk factor that is responsible for the how the asset returns behave, right? And then both of them got Nobel Prize in 1990, much, much later. Okay, so that's the background of portfolio theory. This is where everything started, actually. Okay, so in today's session, I'll walk you through all the formulas step by step in a very connected fashion so that you don't feel left out. Okay, the maths that is there in today's lecture is actually very simple, very, very simple. Don't get scared. It has to just do with two main formulas. One is called expectation, the second one is variance. Once you understand those two formulas, and there is a little bit more, but math does not get much simpler than this. I mean, compared to what we are doing these days, right, with respect to machine learning and other advanced quantitative stuff, stochastic programming, and all these things. This maths today, it looks very, very simple. Okay. But the challenge is to understand those equations in a systematic way. Okay, so when you're climbing the stair, you need to do first climb on the first one, then go to the second one, then go to third one. Do not start with step stair number 5 and then come back to step number 3 and then back and forth. Then it becomes challenging. That is where I find a lot of the literature, they kind of mix up these concepts, but there is a definite pattern in which you should learn the equations. So let's go through those. Okay. So, yeah, feel free to ask me any questions. You can type your question in the chat box. So we have this setup, okay? In our universe, there are more than one asset, okay? At least two assets. There could be more. And then we have some amount, some wealth that we want to invest in those securities or assets. Now, let's assume that both buying and shorting, that means long and short positions, are allowed. Later on, we should be able to restrict, say, short positions, but for now let's assume both are allowed. Long short positions can be possible. Now our goal is to find the best investment by considering both return and risk into account. Remember, Harry Markovich gave us the basically he quantified risk in terms of variance. Now that we have a formula for risk, we can include both expected return and risk into our portfolio selection or portfolio optimization process. Okay. Based on that, what is the best investment strategy? That is our goal. A few more details. These are all housekeeping stuff to make the math simple, right? You see these assumptions over and over and over. When you read about Black-Scholes, also similar arguments are there. So fractional investing is possible. Okay. This is just to make the math simpler. Markets are frictionless. There is no transaction cost, no collateral, no margin. And when we talk about assets, what kind of assets? Assets are all encompassing, right? Everything and anything and everything on planet Earth that is tradable. Those are my, investable universe. Okay. So that includes financial assets like bonds, stocks, or real assets like commodities, real estate. Okay. And even intangible assets like labor market or human capital. Everything that is tradable or has a price is my asset. Okay, so this is my simple setup. Any questions so far, guys? All good? Okay, let's move on then. So here is the thing. This is where I see a lot of the literature. They start with the, when they describe how the portfolio return behaves as a function of individual asset returns. They don't give the proof. The proof is very simple. Okay, so let's go through this. At time t equals 0, you have two assets, asset 1, asset 2. The price of the first asset is S1, price of the second asset is S2. When I say price, it is price per unit. So for example, if these are stocks are easy to understand, then this price is price per share. Okay, price per unit. And then you are holding some units of each of those assets, right? N1 units of asset 1, N2 units of asset 2. The dollar value invested in asset 1 is V1, which is simply number of units times price per unit. Similarly, V2 is N2S2, straightforward. Now, the weights in terms of the value, how much value is invested in a particular asset divided by total value of the portfolio. That's the weight. Why are we calculating the weights? Because the weights will surface in the final equation. We'll see that. Weight of asset 1, when I say weight, it is the value invested in asset 1. So V1 divided by V1 plus V2, and V1 is N1S1. Similarly, weight of asset 2 in the portfolio is V2 divided by V1 plus V2. This is my story at time t equals 0. Okay. Now, after one period t equal to 1, what would change really? Assuming there is no intraday trading or anything, right? I'm holding it. I'm buying and holding those units. So units are fixed. Only thing that is variable, fluctuating every second, is the price, because price is something that is driven by market forces, demand and supply. So S1, S2 will evolve, go up, go down, I don't know. So at the end of this one period, my prices have shifted by an amount delta S1 and delta S2 respectively. Okay, units are same. So the one period arithmetic return, this is important. In Markovich world, we don't use log returns. Log returns have very convenient mathematical properties for other areas. But in Markovich world, it is all arithmetic return. Otherwise, the formula that you know so well will not work. Okay. So the arithmetic return is simply change in price by the original price, right? Delta S return of the first asset R1 is delta S1 by S1. And this is delta S2 by S2. Now tell me something, these returns. So if I'm standing here, sorry, these returns are random. I don't know how much it will be, right? You don't know what the return would be at the end of the period. After the period ends, you will realize that return, because then you would know exactly what is delta S1, delta S2. Okay, so these quantities are random. And there is a reason why I'm taking capital R, right? Sometimes you know, mix up symbols. I also have done it in the past. But as you know, mature, whenever you see random variables, use the capital letter. That is to remain organized. Okay, it's very, very important. Small letters are values. So when you define a random variable, we define it as capital X. This will take a value small x, 1, 2, 3, 4, whatever. Okay. So returns are random. So I have taken it as a capital letter, R1, R2. Now, return will have some distribution. I'm not saying normal distribution yet. We don't need that for today's lecture. But irrespective, there would be some mean, some standard deviation. These are the first two moments, right? First moment is the mean, second moment is the standard deviation. So expected value of return, first return, let's call that mu1. Expected value of the second return is mu2. All right. Standard deviation, you can write standard deviation or variance. Here I have written SD, but yeah, probably I'll correct this, but this is variance. They are interchangeable, right? Standard deviation is the square root of variance. So variance of R1 is sigma 1 square, variance of R2 is sigma 2 square. So this is what we have right now. Now the first question is, since you have a portfolio, what is the portfolio's return? That is also random. We don't know. But very, very conveniently, the portfolio return is simply a linear function of the individual asset returns. Maths is very simple. What is the portfolio return? Portfolio return RP, okay, is total change in portfolio value divided by original portfolio value, arithmetic return of the portfolio, RP. Total change in portfolio value will come from the individual changes, which is N1 times delta S1. That's so the first part is sort of delta V1, correct? Second part is delta V2, right? So N1 delta S1 plus N2 delta S2 divided by V1 plus V2. That's the return of the portfolio. which is random, by the way. Okay. Now, multiply S1, divide S1. Multiply S2, divide by S2. Now, this becomes, if you look at the formula, so delta S1 by S1 is nothing but R1. Delta S2 divided by S2 is R2. N1 S1 divided by V1 plus V2 is W1. Right? In the numerator, we have V1, which is N1 S1 divided by V1 plus V2. So N1 S1 divided by V1 plus V2 is W1. Then N2 S2 divided by V1 plus V2 is W2. All right. So this is where we get this formula that portfolio return is simply a linear combination of asset returns, and the coefficients are nothing but the value weights, okay, of the individual assets. Bashish, do you have a question? Ignore. Okay. Any questions, guys? Simple maths. This is the first equation that you need to know. There is absolutely no complication anywhere, no assumptions. It's a very simple mathematics. Portfolio return is weighted sum of individual asset returns. Everything arithmetic, okay? There is no log return or anything else. Okay, if this is clear, let's move forward. Now, two very important formulas in statistics. And these are probably the most used formulas in all of quantitative finance, but highly, highly underrated for some reason. I don't know why. You won't find these two expressions in books explicitly. I don't know if they assume that you already know them or something, but cannot stress this enough. Two very simple, formulas in statistics which are profound, used everywhere. Always remember them. Okay. So what are those formulas? Expectation of a linear combination of two random variables. Okay. Don't get put off by this mathematics. It's not advanced at all. It's very simple. Let me break it down for you. Expectation of a linear combination. That means if you have two random variables, x and y, and then I create a linear combination of two random variables, alpha times x, you can put a plus or minus, does not matter, beta times y. Alpha, beta are the constant coefficients, x and y are my two random variables. When you have a linear combination like this, what is the expectation of this linear combination? And what is the variance of this linear combination? All right. Now, these formula existed much before. Markovich needed to use those. Why? Because a new random variable is created, which is a linear combination of two random variables. W1 and W2 are the alpha and beta. R1 and R2 are the x and y. Right? At this point, Markovich is like, I need to find because if you have the portfolio return, you want to know what is the mean of that return and what is the variance of that return. For that, you need to borrow these equations from basic statistics. If you look at the documentary, he explains that he remembered the expectation formula, but he did not remember the variance formula, so he had to look up that in the library. It's very fascinating. Okay, so back to the story. So, two formulas. Expectation of a linear combination is simply the same linear combination of individual expectations. Okay, so basically what happens is just take the alpha out, expected value of x, keep the sign as is. If it is plus, keep plus. If it is minus, then keep minus. And then beta will come out, expected value of y. That's the formula. We call this as a linear, expectation is a linear operator because the expectation of a linear combination is the linear combination of the individual expectations. Simple formula. Okay. Two variables. Now you can rewrite the same using matrix formula. So expected value of W transpose X, where W transpose is just the coefficients, weights. Okay. And capital X, when you see things in bold, they mean either vectors or matrices. Okay. So W transpose has the alpha beta coefficients in it, and X is the random variable vector. Then expectation of this linear combination, W transpose will just come out, and then you have expectation of X. So just very quickly, so that you guys are, so W would be like, let's say W1, W2, and this random variable vector could be, say, X1, X2, right? Now, if you write W transpose X, it's simply W1 X1 plus W2 X2. Same thing, this is the linear combination. I have written it in matrix form. So when you have more than two variables, right, 100 variables, 100 different assets, then it's easy to do in matrix notation. And then coming to variance. So variance is not a linear operator. Variance of a linear combination is given by this. Alpha will come out as alpha square, then variance of X. Irrespective of plus or minus, this term is always plus. Don't confuse, okay? Beta square will come out, variance of Y, and then you retain the same sign. If it is plus, then keep plus. If it is minus, then keep minus. 2 times alpha beta times covariance of X comma Y. That's the formula for variance. All right. In matrix notation, same. So if you have a linear combination given in this form, W transpose X, the variance of this is W transpose variance covariance matrix omega times W. These two are same, equivalent. Okay. I'll take show you a concrete example by using two assets so you can understand all the formulas. Okay, so yeah, these two formulas definitely remember all your life. They will help you in a lot of the mathematical derivations. Definitely these formulas would be used. Okay, so remember these. Right, let's move forward. Let me know if you have any questions. Okay, so now back to our portfolio theory. So we have this equation. Portfolio return is weighted sum of individual asset returns. Now, why are we after mean and variance only? Why not about skewness or kurtosis or some other, you know, random quantiles of the distribution like value at risk? Why mean and variance? Those two. Well, it depends on the investor's utility function. So this has a lot to do with financial economics. We'll talk about utility functions later on. But when we say investor has a mean variance utility function, that means all that investor cares about is the mean and the variance. Okay. The utility function means how do you measure the happiness of the investor? That is a function of only mean and variance. That's all that is needed to define the utility function of the investor. Okay. Exact form for the utility function, we'll talk about that later on, not today. There is a very nice relationship actually. Whatever we are doing in Markovitch world can be derived from taking a mean variance utility function. Okay, so we'll see that later. So because investor only cares about the mean and the variance, because those are the things that affect his utility function or happiness, we only need to find out the mean and the variance and would be able to build the best portfolio using those two moments only. Okay, so this is my portfolio return. What is the mean of the portfolio return, expected return? The two important algebraic equations that we talked about, now we're going to use them because this is just a linear combination of two random variables. So expected return of the portfolio, or simply W1 will come out, expected value of the R1 plus W2 will also come out, expected value of the R2, because the expectation is a linear operator, right? So there is a plus sign, you keep the plus sign. Expected value of R1 we have taken as mu1, it's just convenience, and expected value of R2 is mu2. So your final formula for portfolio mean return is W1 mu1 plus W2 mu2. Okay. Similarly, variance formula. Um, Remember the previous formula, right? Alpha square, then variance of x plus beta square, variance of y plus 2 alpha beta times covariance of x comma y. Exact same thing. There is no change. Okay, so you get W1 square, variance of R1 sigma 1 square, W2 square plus sigma 2 square plus 2 W1 W2. Covariance can be also written as correlation times the individual standard deviations, rho times sigma 1 sigma 2. So rho automatically came in. We were not explicitly looking after correlation, but it came in because of the equation or the standard formula that exists, right? And this correlation is the quantification for diversification that we'll see later. So everything kind of falls place in a very neat analytical way. There is no like numerical thing that we have to do. Everything is in closed form, and it's so elegant. Of course, there are a lot of assumptions behind it, but it couldn't be simpler than this, right? So two fundamental equations for expectation and variance. Same thing you can do in matrix form. So let's say you have the weights as W1, W2, weight vector, right? And expected return vector mu in bold is mu1, mu2. Return vector, but this is a random variable. Okay, both of these are random, R1, R2. Variance covariance matrix omega between the two asset returns. You put the variance terms in the diagonal and then the covariance term in the off diagonal terms. And this is a symmetric matrix. Okay, covariance matrix, correlation matrix are symmetric matrices. So in matrix form, your return, portfolio return is W transpose R, just multiply. W transpose would become like this, and R is this, correct? Matrix multiplication, W is W1 R1 plus W2 R2, same thing. This is expected value of this is W transpose is just a constant coefficient vector that will come out. Expected value of R, expected value of R is just mu1 and mu2, which is mu. So if you expand this, it's the same, W1 mu1 plus W2 mu2. And variance is W transpose, variance covariance matrix times W. Please remember one thing. Sometimes people get confused the transpose. Okay. So whatever you have here, the same thing comes out here, and in the variance, the same thing is the first term. And then in this equation, if you take another transpose, W transpose transpose will become W again. So the second term is the transpose of the first term. So what I'm trying to say is, suppose in general, basically, the variance of, let's say, A times X. Okay. A is a vector. X is also a vector. If you have this, then it is the same A will come out. Then variance covariance matrix of X, let's call that omega, then it will be A transpose. This is the formula. Okay. Since I already had W transpose here, that's the one that is coming out as the first term. And then you take the transpose of that in the second term. But if you take transpose of W transpose, it is again W. Okay, keep that in mind. So, right, by default, all vectors are column vectors. So you write it like this. You don't write like W equal to, this is not the convention. Don't write it as row vector. By default, all vectors are column vectors. Okay, that's the convention. So all good so far, I hope. Now, one small question. Why this is not in bold letters, RP? Why is this not in bold? Okay, before that, I have a question. Can you please explain transpose part once more? Okay, sure. Let me do it properly here. So the standard formula for variance of a linear, okay. Um, So let's say A is A1, A2, and X is our random variable vector, which is X1, X2. So if I write A transpose X, it is A1, A2 transpose X1, X2, which is A1, A2. Column vector becomes a row vector after transpose X1, X2. And this is A1, X1 plus A2, X2. In case of Markovich portfolio return formula, we had this, right? If I assume W vector is W1, W2, then this exact same thing can be written as W transpose R, where R is R1, R2. Okay, exact same type of setup. So I can write this in terms of matrix like this. So that part should be clear. Then coming to the variance formula, so the standard formula is like this. Variance of A times X is A transpose variance covariance matrix of X times A. This is the formula. So what I'm trying to say is, if you look at, so in between there is the variance covariance matrix. To the left of it, there is, sorry, I did a mistake. This is not A transpose. We get A transpose here. So what I'm trying to say is, so the basically I'm giving you a trick to remember so that you don't make a mistake. In the middle, there will be the variance covariance matrix. To the left of it, you have something. To the right of it, you have the transpose of that something. Okay. Now, which one is first and which one is last? So how do you remember that? This stuff that you have here is the first term, always. And then you take the transpose of that, put it as the third term. So this is to avoid the confusion between where the transpose belongs. Is it in the first term or the last term? So the trick is, whichever, you're calculating variance of what expression, the coefficient goes here in as the first term as is. There is no transpose. And in the last one, you put the transpose. However, if your expression is this, which is our case, uh, in Markovich portfolio formula, this is our expression, right? W transpose in times R. No worries. The first term comes out as is. There is no change. Then variance covariance matrix. Then you take transpose of the first term, but A transpose whole transpose is A. So we get this. Does that make sense? Now, in case of Markovich portfolio formula, the variance of RP would be W transpose omega W, because our RP is W transpose R. That's why. Perfect. You should ask these questions. Do not hesitate, because this is a very fundamental class. Things will get real dirty real quick going forward. Okay. So that's why I'm taking it slow. So we are clear with this. Coming back to my question, why do you think RP is not in bold? Or is it a mistake that I did? In the matrix formulation, everything is in bold. W is bold. Expected return vector mu1, mu2 is in bold because it's a vector. This is a return vector. This is a matrix, full-blown matrix. But RP, portfolio return, yes, exactly. So please remember that it is already a linear combination of two asset returns. The output would be one single number, 5%, 10%, which is the portfolio return. So it is a univariate random variable. Okay, it is not a vector of random variables. That's why it is not in bold. Just a univariate uh, random variable, like one single normal distribution, not two different normal distributions. Okay, now let's move on. Now let's talk about So in this, so what we'll do next is we'll start with a very simple portfolio, derive the risk return characteristics, and we'll do a lot of experiments, and then we'll start complicating the portfolio. Okay, slowly and steadily. Very nice equations come out. I see in some of the books, in the first or second page, they start with the capital allocation line, efficient frontier, and CML, tangency portfolio, all these things without doing all these maths. I don't understand why. Everything flows very naturally, okay? So we'll go step by step. Remember, climb the first step, then second step, then third step. So our first experiment is, in our portfolio, there are two instruments or two assets, one risky asset and one risk-free asset. Risk-free asset is a misnomer, actually, but it is the cornerstone of a lot of financial arguments, including pricing of derivatives. You need a risk-free asset. Okay, but does it really exist? Nobody knows. Maybe not, but it makes the math so easy, and there is a whole breed of arguments called no arbitrage pricing. So anything that is risk-free is supposed to give you a risk-free rate. That's the argument. So we need the existence of a risk-free asset. So let's assume that there is a risk-free asset. Now, what is a risk-free asset? Risky asset, we understand. Risky asset is something that will have some, basically the return is random and it will have volatility variance, then it is a risky asset because we quantify risk as variance. That's all we care about, right? So if it is a random variable, then it will have variance, so it is a risky asset. A risk-free asset has returns which is not random, obviously. Only then it will be risk-free. But this statement is not fully true. But however, in this context, let's assume that. Okay, so what is a risk-free asset? It has these three characteristics. It has constant return. Let's call it RF, risk-free asset. A return is RF. No volatility is zero, constant return. And then the correlation is zero with every other risky asset. Obviously, if this is always fixed, it is not correlated with any other asset's return. So that is my risk-free asset. Okay. Now, when it comes to this portfolio where we have two assets, one is risky, the other one is risk-free, it makes things very easy to understand if we put everything in a diagram. Typically, we plot the risk return characteristics in form of a XY plane, where in the x-axis we have the risk. I'm taking standard deviation as the risk measure. You can take variance also, but this is the convention. And then mean return in the y-axis. So the two assets that I have in my portfolio belong in this plane. So you can see asset A here is here, which has a risk of sigma a return of mu A. So this is a mean return. Please remember, when you say just return, it is confusing because return is random. When you say mean return, it makes sense. It's one statistic, right? So this is where my asset A is, and then there is a risk-free asset, which is here. Risk is zero. The x coordinate of asset B, which is the risk-free asset, is zero because there is the volatility is zero. And it only has y coordinate, which is RF. Okay, so these are the two assets in my portfolio. This is how they look like geometrically. Now, let me invest WA. So the weight of investment is WA and WB respectively for asset A and asset B. So the weight of the A is WA here. And the weight of WB is obviously 1 minus WA because the sum has to be 1. All right. Now, let's derive the return and risk characteristics of the portfolio. And let's see what is the set of points that I can achieve in this particular plane. So the freedom that I have is to tune this thing, WA. How much weight I want to invest in A, that is up to me, completely in my hands, correct? So I can alter WA is like a knob. It's like the volume button on your radio. and you can tune it as per your desire. And the resulting portfolio will have different risk return characteristics. So let's explore that by tuning WA. If you change WA, obviously you're changing the weight on B also because it is 1 minus WA. How is the portfolio going to behave? So let's see. Okay. 1 second, guys. All right. Math is again very simple. The same stuff that we did, we'll just reuse it. Expected return of the portfolio is W1 mu1 plus W2 mu2. In our case, it is WA mu A plus 1 minus WA, which is the weight of on asset B. But asset B has a mean return of RF. Well, it is mean return because it is a constant return. So if you have a constant with random variable, which is a constant, then that's the mean, right? So we get this and just rearrange. Take 1 times RF would be RF, and then take WA common, you'll get mu A minus RF. Okay. So we can see that so here is the same thing. The mean return of the portfolio is RF plus WA times mu A minus RF, right? I put the WA in terms of orange color because that is something we can control. It is completely up to us. The amount that we want to invest in asset A is totally up to us. So you can think, so these characteristics are part of the assets, RF, mu A, sigma A. I don't control them. I can choose different assets. Yes, that is up to me. But once I've chosen those assets, now the next step is to choose the investment. That is up to me. So there's a question, why don't we call the return of B as mu B instead of RF? Is it an assumption? So risk, I mean, it's just a notation. Because it's a very special asset, right? It's not just any other asset B. It is a risk-free asset, right? So that's my asset B. So risk-free asset has a return of RF. That's all. Because we're going to use the risk-free asset later on. So the portfolio is going to get complicated. Okay. Risk-free asset, risk-free return is a very, very important contributor to portfolio dynamics and derivative pricing. So it requires its own symbol and treatment, if that's your question. Okay, so that we don't confuse this with any other generic asset. It's a very special asset. Okay, now variance, right? Standard formula, you get WA square sigma A square plus 1 minus WA square times the sigma of the risk-free asset is 0. Correct? So this is 0. And then the second term is also 0 because the correlation is 0 and there is also sigma B which is 0. So the second term vanishes and we have a very simple expression WA square sigma A square. Essentially the first term. This is the term that remains. So you take the square root, portfolio volatility is WA times sigma I. So these are my governing equations for the portfolio dynamics for mean return and volatility. Now, both of these are parameterized by WA. What does that mean? WA is something I control as an investor. So I can keep changing WA that alters mu P and that also alters sigma P. So they both change simultaneously as and when I change WA. So the question is, how do they change together? What is the equation that binds mu P and sigma P together? Do they move in a circle or is it a straight line or is it parabola, hyperbola? What is ellipse? What is it? Individually, we can see that mu, the mean return, is a linear function of WA, proportional, right? So this is a constant term and there is a sort of a slope here and then just multiplied by WA. So if I change WA, the mean return also grows linearly with respect to WA. Same with standard deviation of the portfolio, also grows linearly because it is just WA times sigma of the risky asset A. Okay. Now, when you have, I don't know if you have done this before. So when you have um, x and y parameterized by some other parameter, how do you derive the equation? It's very easy. The equation of a straight line is y equal to mx plus c. Everybody knows that, right? C is the intercept, m is the slope. This equation is y equal to mx plus c. And m is the slope. C is the y intercept. Okay. Now, this is a relation. So you need a relation between y and x to plot that line, correct? But if I don't give you an equation like this, instead, I give you two different equations, one for x, one for y, then you have to eliminate the common parameter and derive the equation. It's very easy, guys. Don't get afraid. I'll show you. So for example, let's say x equal to a times t, for example, and y equal to b times t. T is the parameter that is changing. A and B are constant. So if T changes, X changes, T changes, Y also changes, X and Y change together. What is the relationship between X and Y? Very easy. Divide Y by X. T gets eliminated. You get B by A. So Y equal to B by A times X. This is the equation of a straight line, but passing through origin. No intercept. B by A times X. B by A is the slope. Right? So sometimes so this is called parameterization. X and y are parameterized by t. You eliminate t, then that gives you an equation between x and y, and you can easily plot that. Something similar we have here. So let's go back. So we have mu p equal to rf plus wa times mu a minus rf. Let me write it down. Mu p equal to rf plus weight in asset A times mu a minus rf. And the portfolio volatility is WA sigma A, correct? I want a relationship between mu P and sigma P. How are they related, right? So if the volatility of the portfolio increases, the mean return ideally should increase because that is the classic risk return trade-off. You take more risk, on an average, you are supposed to get more return, right? That's the basic assumption. But how do they change? Is it proportional change? That means linear change, or there is some non-linearity. We have to find that out. Eliminate the common parameter that I'm controlling. That's it. So I can write mu p equal to rf plus, replace wa from the second equation, that is this, and you get this, right? Y coordinate, y equal to some constant, which is rf plus slope times sigma p. Actually, let me not write y. Uh, let's keep mu p. Okay, so the RF is the constant, and so we are trying to establish a relationship between portfolio mean return and portfolio sigma, and this is it. What is the slope? So our constant is RF. What is the slope? The slope is mu A minus RF divided by sigma A. So clearly we can see that the mean return is a linear function of sigma P. All right, and if you want to plot it, it will be a straight line. But since there is a intercept, so it will start from RF and the slope is this guy. And that's how the portfolio return and risk would be related, or mean return and volatility would be related in a linear fashion, which is kind of nice. Okay. The slope, if you look at the structure of this, we'll come to this later, but I think pretty much all of you know how this looks like. We have a name for it. And this is not an accident. This has far-reaching economical um, consequences. We'll talk about that, right? Yeah, exactly. This is Sharpe ratio. We'll come to that. So it is not an accident. That slope is some weird quantity. That's not the case. So let's come back. So we finally figured out that the profile, risk return profile of the portfolio would be a straight line. Intercept RF with a slope of, so here is the question, sigma, slope is mu A minus RF by sigma A. Okay, now, just quick sanity check, right? If WA is equal to 0%, that means your entire investment is in the risk-free asset. Your entire investment is in the risk-free asset. Then what do you get? WA is equal to 0, so mu P is equal to RF. The mean return would be RF because it is you only have the risk-free asset. There is nothing else. And sigma P would be 0. So that corresponds to this point. So the left extreme point on the line corresponds to a portfolio which is 0% invested in the risky asset and 100% invested in the risk-free asset. The right extreme point on this profile corresponds to the risky asset A itself, where there is 100% investment in risky asset, no investment in risk-free asset. Let's put WA equal to 1. See what happens. Mu P is equal to RF will get cancelled. Mu, right? WA is equal to 1. So RF will get cancelled. You get mu A. That's the return. And sigma P would be sigma A. So you get the other extreme point. If you take a mix of both, so let's say 50% B, 50% A, then you will be somewhere here. Okay. It's linear. So all I'm trying to say is, of the entire spectrum of all kinds of risk returns characteristics that you could get, right? You cannot span the whole XY plane. You can only span a line. You are allowed to be anywhere on this line, not outside. You cannot come here. You cannot have a risk return profile which is like this, right? This is the risk and this is the mean return. That's not possible. You can only travel along this line. Does that make sense? Everyone clear? Any questions? Okay, no questions. Then let me quickly demonstrate the same in Excel. Some folks have a strong affinity to see everything in Excel. So right, one risky asset, one risk-free asset. So here is the risky asset A. The mean return is 10%, volatility is 20%. Risk-free asset, we only have the RF, which is mu B in the case, as you mentioned, Somitri. 5% is the risk-free return. These are the two equations that we developed. So the variable that we control is the asset allocation, WA. And accordingly, the mean return and the volatility will change based on these two equations. Right? The intercept is RF, 5%. The slope is mu A minus RF divided by sigma A, which is 25%. Now, these are some of the discrete points that I took. So just changing WA, starting with 0%. Remember, we are operating. So in this case, we're operating under the assumption that there is no short position. You can only buy, right? So there is no negative weight. So WA can go from 0% to 100%. And then correspondingly calculate mu P according to this equation and sigma P very simply according to this equation, right? And if you do a plot between mu P and sigma P, you get this. This is the scatter plot, but it is a straight line. At the two ends of the spectrum, we have the risk-free asset here, 0 volatility and 5% return. And we have the risky asset here, 20% volatility and 10% return. As a portfolio, you can be anywhere on this line by making a suitable adjustment to WA. Okay, any questions? Gaurav has a question. The Sharpe ratio and sigma of the portfolio has a linear relationship, or the relationship can be non-linear also. Sharpe ratio and sigma of the portfolio. Um, we will get to that. I have not explored Sharpe ratio yet. Let me get there, and then we can have the discussion. At the moment, I don't have a straight answer to your question. So let me get there, and then we can talk about that. Okay, before that, did you understand this setup? Is it fully clear, guys? Any questions? Simple portfolio. Okay, let's move on then. One small enhancement, and then we'll take a break, and then when we come back, we'll deal with more complicated portfolios, and we'll see very interesting risk return profiles. Yeah, so let's talk about this. Same setup, but this time we allow short positions. Okay. If you're only allowing buy positions, then you can move between these two extremes, B and A. However, if you allow short positions, I can short the risk-free asset, which is same as borrowing at risk-free rate, because you are not putting your money, you are borrowing. So it is like shorting the asset, which means you are borrowing at risk-free asset, and whatever money you got, you invest in A. So it creates a leverage position in A. Okay, you are shorting the asset, risk-free asset, and you are investing heavily on A, right? If you allow to do that, you can move further. Along the same line, you are allowed to move further. That means you can get portfolios which are riskier than A and also have a higher return than A. Okay, so please note that this point is where there is no allocation to A. And this point is where there is 100% allocation to A. In between, the allocation is of for A is between 0 to 100%. If you allow B, weight on B to be negative, that means short position on asset B, then you can have WA more than 100%. So for example, WA could be 150%, and so WA could be 150%, and WB could be minus 50%, short position. Together, they always have to add up to 1. That you cannot violate that constraint, right? So in this leverage position, you can get out of this bounded zones and then have portfolios which are riskier, but also at the same time give a higher return, right? So yeah, that's what I'm saying here. And then quickly go back to Excel. The only thing that I did here is increase the weight of A from 0% all the way till 200%, right? And then you can have additional portfolios with a much different risk return characteristics. Still, you'll be operating on this linear line. You cannot go outside of it, but it lets you uh, go out of these bounds basically. Okay, it can be anywhere on this line. That's it pretty much. Okay, any questions before we take a break? Okay, let's meet after 5 minutes. Thank you. All right, let's continue with our experiments. Next, what we'll discuss is we talked about no short selling and short selling allowed conditions, and then right. So here there is I have a question for you as a homework. Okay, so think through this and figure out. instead of shorting the risk-free asset, what if we short the risky asset and create a leveraged position on the risk-free asset, right? So that's the question. So try to figure out how would this work. That's the homework. All right. Now let's talk about a more practical portfolio where we have two risky assets. Okay. Two risky assets. So let's park the risky asset for now. We'll think about that later. Now let's consider that our portfolio has two risky assets, asset A and asset B. The weights invested in asset A, asset B are WA, WB. Obviously, WA plus WB equal to 1. And in the risk return spectrum, this is how they look like. So A has a little higher risk, so higher mean return, and B has a little lower risk, so little lower mean return. Now the question is, what can I change? So I only have these two assets. These are all given to me. Mu A, mu B, sigma A, sigma B are the characteristics of the asset returns. I don't control that. Okay. God controls that. The randomness in the assets. I don't have any control. What I can control is the investment amount. Investment amount in each of these assets. That is what I control. So WA is the single parameter that I control. By changing WA, I'll get different portfolios. What are the So if you get different portfolios, you get different associated mean return and sigma of the portfolio. Question is, how does the profile look like? What kind of portfolios I can generate using two risky assets? Okay, so let's do this. Equations again, same age-old equations, nothing has changed. The expected value, expected return of the portfolio is W1 mu1 plus W2 mu2, which is in our case WA mu A plus 1 minus WA times mu B. Remember, there is no risk-free asset here. Both are risky. And just rearrange. Mu B take outside plus take WA common. You get mu A minus mu B. This is the setup is similar. Instead that you have mu B instead of RF. Coming to the risk side, variance of the portfolio, you have the full-fledged variance equation. There is no simplification because everything has variance. So we cannot do anything. You just keep it as is. And there is a correlation also, rho that will come into picture. So these are my final formulas for portfolio mean return and portfolio volatility. Both are parameterized by a single parameter WA, which I can tune, right? I can tune. Okay, now if you can, so here's the thing. Clearly, this looks like a nonlinear equation because you have the square root and WA square, all kinds of stuff happening here. So the idea would be you should do this sigma p equal to, in this expression, replace WA from the first equation. What is WA? WA is mu p minus mu b uh, divided by mu a minus mu b, correct? If you take this expression for WA and put in the second equation, then you have an equation between sigma p and mu p. Correct? This is the x coordinate of the portfolio return. This is the y coordinate of the portfolio return. Basically, this is the risk which is in the x-axis. This is x. This is y. So you get a relationship between y and x, or x and y. And that, looking at the equation, you would be able to tell if it is linear, circle, ellipse, parabola, hyperbola. We don't know. Okay. So if you want to do that, go ahead. But let's not do that. Instead, we will do one thing: plot both of these for varying by varying WA, exactly how we did in the Excel, and we'll see how the profile looks like for different values of WA. Okay. Acha, before that, we also have this row. Rho is something that you don't control. Okay, when you have the assets, the correlation between the asset returns is zero. You don't control it. However, for different values of rho, you get different diversification benefits. Okay, remember what I told. The quantification of diversification is correlation. So if you look at correlation values, we know that correlation takes a value between -1 to +1. If you have rho equal to -1, you get maximum diversification. Your portfolio volatility will go down. And if you have rho equal to +1, which is the other extreme, that means assets are perfectly positively correlated. There is no diversification benefit. Okay, so your volatility of the portfolio will be highest in that case. Okay, now please remember that the volatility of the portfolio is bounded between these two extremes. This one corresponds to rho equal to -1, and this one corresponds to rho equal to +1. Everything in between is, so these are the two extremes. This is very simple, guys, and you all must remember this. What is the variance of the portfolio? Sigma p square equal to, say, W1 square sigma 1 square, W2 square sigma 2 square, 2 W1 W2 rho sigma 1 sigma 2. If, so case 1, rho equal to +1, then sigma p square becomes the, look at the last term. Last term will become 2 W1 W2 sigma 1 sigma 2, right? Isn't that this? Clearly, right? A square plus B square plus 2AB, all of those are there. That's A plus B whole square. Okay. And the volatility, so here is one thing very, very, it's a trivial thing, but important thing. What is the square root of a square, guys? Let me see how many of you get this right. What is this quantity? Okay, positive x plus minus x plus minus x x. Positive x is right. The answer is this, mod x. Okay, because please remember, square root as a function always returns a positive number. You go to Excel, write square root of 25, it will not give you -5, it will always give you 5. When you're solving the roots of an equation and you end up with x square equal to 25, then you have two roots, x equal to +5 or x equal to -5. But if somebody asks you, hey, what's the square root of 25? You never say -5, it is always 5. Okay, so in that case, if x is positive, say let's say 5, 5 square root is 5, no doubt about that. But -5 square root is also 5. Combine these two, right, is it has mod x. That takes care of both cases, right? It's always absolute value of x. So it remains positive. Sigma p is W1 sigma 1 plus W2 sigma 2 mod. This is important because when you take short positions, if you're not putting absolute value, it might happen that the whole quantity becomes negative and you report portfolio volatility as -20%, which is ridiculous, right? Always remember, square root of square is absolute value of that entity. So this is one extreme, and the other extreme is rho equal to -1. Asset returns are perfectly negatively correlated. You get maximum. I get Copilot icon everywhere now. I mean, I don't know. I have mixed feelings about it. It's kind of obstructing. In these symbols also, I'm getting Copilot link. Anyways, okay. Um, Sigma. What is sigma p square in this case, guys? A square plus B square, rho becomes minus 1. So minus 2AB, that's just A minus B whole square. A minus B whole square. Sigma P is W1 sigma 1, W2 sigma 2 mod. Okay, so these are the two extremes. This is the highest possible volatility. This is the lowest possible volatility. And then for different values of rho, you get a value in between these two extremes. Okay, all right. So this is one important insight. Now, coming back to our profile, what kind of portfolios you can create out of it? Do they all lie on a straight line or something else, right? It will not be a straight line. As you can clearly see, it is a highly nonlinear relationship. So let's do it in Excel. But before that, let me show you. Let's talk about a few things and then I'll show you the calculations in Excel. It's easy, nothing difficult. The profile that you get is a hyperbola. It's a hyperbola. Okay. So A is here, sigma A mu A. B is here, mu B sigma B. And when you take a combination of A and B by changing the weight, right, on any asset, WA, then you get various. So here I'm assuming short position is allowed. Okay. If short position is not allowed, then you will move between B to A. Those will be the two extremes. But if short position is allowed, then you can move outside of B and A. Exactly how we saw in the first case. But this is the profile you get. It's a hyperbola. Okay. You can, by choosing WA appropriately, you can be anywhere on this particular curve. It's called as the opportunity set. Opportunity set means you have the opportunity to be anywhere on this curve, right? Any point you choose, you can be there on this curve. What about a point outside of this? You cannot get there. It's not possible. With this portfolio with two risky assets, you are bound to move along the curve. Okay. Now, this at this particular point, 100% weight is allocated to A, no weight is given to B. At this point, 100% weight is given to B, no weight given to A. If you go further in this direction, you're creating a leverage position for B. That means you're shorting A, investing more on B. That means the weight of B would be more than 100% in this direction. And A will have a negative weight. In this direction, from beyond A, right? So you invest more heavily on A. That means you short B and more than 100% allocation to A. So let me just summarize. So maybe I can write on in this zone, WA will be greater than 100% and WB will be negative 0%. And in this zone beyond B, WA would be negative and WB would be more than 100%. Remember, together the weights have to add up to 1 always. And in between A and B, this part of the curve that you see, it's always WA is less than 100%. Actually, between 0 to 100%, and WB also is between 0 to 100%. Okay, so that's it's very interesting. We get a hyperbolic profile. You can be anywhere on this curve. All right. Now let's explore the important parts of this particular curve. The first fundamental question would be, if you see this curve, right? The question is, are all points on the curve equally efficient? That's the first question. What does that mean? All points on the curve, are they equally efficient? What is the answer, guys? Yes or no? Answer is no. Okay. Why? Efficiency means for a particular level of risk, you should be able to get the best return possible. That means if you have two securities for the same risk, one is giving return which is mu1 here, another one is giving a higher return. This is inefficient, this is efficient. Simple stuff. Why would I buy this? I'll always go for this. Same level of risk. Remember, as an investor, my utility is fully defined by mean return and risk. I don't care about any other attribute. Those two define my utility function. Now, for a given amount of risk, if I'm getting higher return, right, higher mean return, then why would I choose the other asset, right? So this is inefficient and this is efficient. Now I have a spectrum of different portfolios. So you can clearly see that. Actually, let me go to the next slide. You take any value of risk. There are two possible returns I'm getting. One portfolio is here, another portfolio is here. Both of these portfolios have the same risk, but this portfolio gives me higher mean return than this. So this is inefficient, correct? So if you only look at portfolios which are efficient, that means for a given level of risk, they give the highest possible return. Then we're looking at the red part of the curve. I've highlighted the portion of the opportunity set which is efficient in red color. Starting from here to upwards, this side is inefficient. Is that understood, guys? Any questions? Okay, so yeah, so this red part is called as efficient frontier. It's a subset of the opportunity set which is efficient. Okay, all right. Now, on this efficient frontier, there is a very special portfolio which gives you minimum possible variance. And that point is here, the green one that is highlighted. That is the portfolio which has the least risk. You cannot get a lower risk than this. Correct? This is called as GMVP, Global Minimum Variance Portfolio. Okay, and that's the beginning of the efficiency, right? So for that minimum variance, there is only one portfolio possible. There is no you cannot have any other portfolio. It's just one portfolio which has that minimum variance, and from that, that is the one end or the beginning of the efficient frontier, and then you go upwards like this. Okay, so how do we find out this particular portfolio? Remember, all portfolios are parameterized by the single parameter, which is WA. By changing the knob, right, WA, I am generating all these portfolios. So what is WA that leads to GMVP? That's the question. The answer is this. The weight that you need to invest in asset A that will lead to the GMVP is given by this. Now, should we derive this? Again, don't be scared of maths. This is all the maths that we're doing today is very, very simple. Okay, basic ideas. It's not complicated. So let's quickly derive this. It's easy. It's just a simple minimization exercise. What is the portfolio variance? Sigma p square equal to WA square sigma A square 1 minus one single variable. Okay, it's a univariate optimization problem. The variable that we can change is WA. That's all. There is no other parameter. This is my portfolio variance. To attain minima, the derivative with respect to the independent variable would be 0, right? So differentiate both sides with respect to WA because that's the variable that is controlling the value of sigma p. So if chain rule, okay, 2 sigma p d sigma p by d, not sigma, dwa, correct? 2 sigma p times d sigma p by dwa equal to, so I'm differentiating everything with respect to wa. 2wa, all the other parameters are constant. Plus 2 times 1 minus wa sigma b square. One moment. The coefficient of w is negative, so there will be a -1, right? So I will just change this to minus, plus 2 rho sigma sigma b, I'll take outside constants. Derivative of wa times 1 minus wa with respect to wa. So if I open it up, the first term is wa, derivative is 1, minus second term is wa square, derivative is 2 wa. Okay. This will be 0 for minima. So the entire expression is 0. So this implies, let's take wa, let's do one thing. 2, 2, 2, let's cancel out. Take wa common, we have sigma a square from here, then minus minus plus sigma b square from here, right? Then minus, so there is a 2 rho sigma a sigma b, and then we have, what are the constant terms? We have a minus sigma b square, and here we have rho sigma a sigma b. This equal to 0. So we get our allocation that leads to GMVP is equal to, they take these two to the right hand side, take sigma b common, we have sigma b minus rho sigma a divided by sigma y square, sigma b square, 2 rho sigma a sigma b. This magical allocation to asset A will lead to a portfolio which has the least variance. All right. Sorry, I'm a little bit under the weather. Okay, so derivation is very simple. So that's the formula for GMVP. Now, putting all these into, uh, let's see. Yeah, let's go to Excel and just verify these calculations quickly. So here I have two assets, two risky asset portfolio. Asset A, mu 8%, sigma A 20%. Asset B, mu is 6%, sigma is 12%. So low risk, low return, high risk, high return. Correlation is 0.4. I should be able to change it. Okay. This is the y coordinate of the portfolio return, which is the mean return. Mu p is given by this formula. And this is the x coordinate, the risk of the portfolio, sigma, right? This is the formula for GMVP, and I'm applying the same formula, or everything is given. So just using the formula to calculate what is the allocation to asset A that will lead to GMVP. And with that allocation, you can calculate mu p sigma p, because once you decide on the allocation, mu p is given by this and sigma p is given by this. Just plug in the value of WA, which is this one that is coming from the GMVP formula. So these are the mean and sigma associated with the GMVP. Okay. Now let's look at the plot. Exactly, we're getting this plot, hyperbolic plot. This is the point which is GMVP. You can see 11.72% is the sigma, 6.27% is the mu. This is the minimum possible sigma that you can have, right? And from this point onwards, we have the efficient frontier. Getting this plot is very easy. It's just taking values, different values of WA from minus 100% to plus 200%, plotting the mu and the sigma, and then this is just a simple scatter plot with joining every points with a line, and then this is what you see. Okay. Any questions? Okay. Yeah. So let's look at a few cases of this particular portfolio with different values of rho. Okay. So case one, rho equal to plus one. Okay. Excuse me. If rho equal to plus one, then what happens to the mu p and sigma p? I'll probably need 15 more minutes to wrap up this. Okay, so case one is rho equal to one, and there is so this means no diversification benefits. No diversification. Assets are perfectly positively correlated. Okay. Um, yeah, let's go back to the slide. I have everything here. The equation for mu p remains the same because mu is not affected by correlation, right? Mu remains the same. For sigma p, remember, if rho equal to 1, we get a a plus b whole square, right? And then the square root, which is absolute value of sum of the these two terms, correct? In case of rho equal to 1. So just rearranging it. So keep sigma b plus take, so replace w because there is only one weight that we are controlling, right? Automatically wb gets adjusted when we change wa. So wb is 1 minus wa. So just sigma b will come out, and then take wa common, you get sigma a minus sigma b, right? So if you do this, then the hyperbola actually becomes a straight line. The reason is A and B are not very different assets. If there is a perfect positive correlation, pretty much they are like the same asset, right? If it's the same asset, then you get a um, straight line. So let's just go to the Excel and experiment. So here, if I change rho to plus one, the hyperbola becomes a straight line. Okay, right. So you can move along anywhere on the straight line. You can choose to be between A and B. You can also go further down or go up if there are short positions that are allowed. And it is possible to have a zero variance portfolio. Okay, the GMVP, Global Minimum Variance Portfolio, will have a variance of zero. It is possible. Okay, and what is that value? It's very easy. So if you look at sigma p equation, when does sigma p become zero? For what value of WA? WA equal to sigma. So this whole thing will be zero, right? Sigma B divided by sigma B minus sigma A. With this allocation to asset A, it will lead to a portfolio that has zero variance, which is very, very interesting. You are creating a risk-free asset. If there is perfect correlation, you can do things like this. Create a asset which is zero risk. But this would include short position. So in this picture, you can see it's a short position in A and long position in B. It's a leveraged position of B. That will lead to global minimum variance portfolio, and the minimum variance in this case is exactly zero. Okay, let's verify that in our Excel. In this case, look at the GMVP. The volatility of GMVP is zero and gives a return of only 3%, which is lower than the than mu B is 6%, right? So if you absolutely hate risk, like you cannot have any risk, then we can have this kind of portfolio. No risk, you get a 3% return. Yes, you compromise on your return side. You could have got 6%, but then if you don't have any tolerance to risk, you should go ahead with this. And you can clearly see it's a short position in A, minus 150%. What is the allocation to B in that case? It's a short position in A. What is the allocation to B? 250% plus 250%. Yes, it's a leveraged position on B. Okay, so that's case one. Let's go to case two. Case two is rho equal to minus 1. This is when you get maximum diversification benefit. The equation for mu is the same. There is no change. Mu does not depend on correlation. Then sigma p has this formula, right? It will be a minus b whole square and then absolute value of a minus b. Just rearrange, you get this expression. Now, in this case also, you can get a zero variance portfolio. The GMVP would be a portfolio with zero variance, and the allocation for that is sigma b by sigma a plus sigma b, making this thing equal to 0. But this is much better than the previous one. Why? Who can tell me? Getting a zero variance portfolio in case of rho equal to minus 1 is a much better portfolio than the other zero variance portfolio which we had in case of rho equal to plus 1. Why? So Pnil says correctly, we are getting it without shorting. Yes. Look at the formula for the weight allocation. It is positive. The allocation given to A is positive and it is also less than 1 because sigma b, obviously denominator is bigger than numerator, so this is a fraction. So you have buy position in both of these. There is no shorting. If you do that, please remember your mean return will fall between B and A always. If you have buy positions, then you are between A and B. If you are shorting, then you are going outside of A and B, depending on which side, right? So in the other case, we had a very bad return. Zero variance, yes, but the return was like 3%. Now we'll get the same zero variance portfolio, but in this case, our return will be higher. It will be between 6% and I think it was 8%. Let's look at that. Rho equal to minus 1. It's an extreme hyperbola case, right? The allocation to asset A is 37.5% positive. Allocation to B would be what? 62.5%, I guess. Mean return is much better, 6.75%, risk free, right? That is the power of diversification, full, complete diversification in this case. It's much better, right? Okay, so these are the two extreme cases. And then in between, you have very interesting portfolios which are like proper hyperbola. So 0.5, you get like this with different correlation values. You get different hyperbolas. And please remember that all your portfolios would lie on this curve. It cannot be outside of this. Okay, you don't have the whole XY plane to play with. You only have a line, and you can only travel along this line, right? Yes, correlation of -1 is just a myth. You can get close, but yeah, that's what asset managers are always looking after: high alpha, diversification, and all these things. All right. So yeah, I think this is we're all good with this. The last topic for today's class is something around the Sharpe ratio. Give me 1 second. Okay. We have not forgotten about the risk-free asset, right? So we had that earlier. Now let's bring it back. So now we have the two risky assets. On top of that, we also have access to that risk-free asset. So three securities. Okay. Now understand this. So when we had remember the first use case where we had a risk-free asset and a risky asset here, A, right? Combining a risk-free asset with a risky asset, the kinds of portfolios that you get is a straight line. You can be anywhere on the straight line. Obviously, if you want to go beyond, you have to short the risk-free asset. But the main thing is when you combine a risk-free asset with a risky asset, the resulting portfolio has a mean return and risk profile which is linear, joining these 2 points, correct? So if we have the risk-free asset and a risky asset, now the risky asset in our case is a risky portfolio of two other assets, A and B. This hyperbola is a spectrum of different kinds of risky portfolio I can create by considering various proportions of A and B. So what I'm trying to say is, now pretend that the two risky asset portfolio as one single risky asset with its own characteristic mu p and sigma p that we derived in the last section. Okay, consider the risky portfolio as a risky asset. Now we are mixing that with the risk-free asset. So for example, this particular point, okay, it's a risky portfolio consisting of some kind of proportion of A and B, right? And then when you combine with the risk-free asset and the risky portfolio, you get a straight line which joining the risk-free asset and the risky portfolio. This red line. Make sense? The only difference is it's not a single risky asset. I have a whole range of possible risky assets because I can tune the weights of A and B and move along this hyperbola. I can choose my risky portfolio to be anywhere on the hyperbola, and I can join that with the risk-free asset. Right? Make sense? So I can choose this risky portfolio, and then if I combine risk-free asset, I'll get a line joining these 2 points. Okay. Now tell me one thing, common sense. Which risky portfolio is the best to be combined with the risky asset? So let me plot it here. I have, with the two risky assets A and B, I have a nice hyperbolic profile. My risky portfolio can be anywhere on this hyperbola, right? And then I'm mixing that risky portfolio, which is not just one. It can be any risky portfolio on this hyperbola. This is one risky asset. I'm combining this risk-free asset. Um, I can choose this. If I choose this, which has a fixed composition of A and B. Please remember, A and B are the constituents of the hyperbola. I can get this line. If I choose this point, I'll get this line. Which is the best risky portfolio that I should choose to combine with risk-free asset? As all of you said, it is the one that becomes the tangent to the hyperbola. This point, so basically, so if you are not engineers, that's fine. But if you are engineers, we have done this exercise, how to draw a tangent from a particular point to a curve, right? The fixed point is here, risk-free asset. We just want to draw the line which is tangent to the curve. Tangent means it just touches the curve. No intersection, just touching. This is the point of tangency. This is the best risky portfolio that we want to mix with the risk-free asset, because combining these two gives me the best efficient frontier. Actually, not best efficient, it's kind of redundant. The new efficient frontier is not on this hyperbola. So earlier we had this line, right? So from global minimum variance portfolio, from here to here, this was our efficient frontier. But we have something better now. By combining the risk-free asset, my new efficient frontier is, let me draw with a green line maybe. This is my new efficient frontier, guys. It's better because for any risk level, this line gives me the best returns. Take any point. My old efficient frontier would have given me this return, but now by combining the risk-free asset, I'm getting this return, which is even more efficient, right? So the green line is our new efficient frontier. And that is the best you can have, because you see, you cannot escape the hyperbola. With the risky assets, you are bound to be in the hyperbola. So you will always have a point, no matter what profile you get, right? What straight line you make, it has to either touch or intersect the hyperbola. You cannot be above the hyperbola all the time, because the risky portfolio has to be on the hyperbola. So the best you can do is if you choose the tangent, right? It's also called as the tangency portfolio. So this particular point is called tangency portfolio. Okay, so the optimal mix is the with the risk-free asset is the portfolio which is at this particular uh, point of intersection between the tangent and the hyperbola. That's the portfolio I'm looking at. Okay, and this green line is my new efficient frontier. Okay, all right. Now coming, yeah, give me 5 to 10 more minutes max. How do we draw the equation of this line? How do we draw the equation of this line? So let's do this. Let me redraw this. We have the risk-free asset here. Choose any portfolio C, not tangency portfolio for now, any portfolio C on this hyperbola, right? Which is a suitable combination of weights between A and B. And if you combine risk-free asset and this risky portfolio, you can get a risk return profile like this, which is you get by joining these 2 points, correct? What is the slope of this line? Very easy. Mu P is, let's say the um, weight invested in C is WC. Weight invested in risk-free asset is 1 minus WC. So 1 minus WC times RF plus WC times mu C, correct? or you can rearrange and write as RF. This already we have derived before. So take WC common, you get mu C minus RF. This is the equation for mean return. And for the sigma P, remember risk-free asset has no volatility and there is no correlation. So it's simply weight on the risky asset. In our case, it is C times sigma of C. Eliminate the common parameter WC, and we get the equation of the line, which is mu P equal to RF plus mu C minus RF divided by sigma P. Oh, not sigma P, sigma C times sigma P, right? So mu P is related to sigma P. So the overall portfolio. Now, please remember our P portfolio consists of the risk-free asset and C together. Inside of C, there are two assets A and B. I'm not worried about that right now. Okay. The portfolio return P and the sigma P are related using this straight line, right? Linear equation, constant intercept, and then there is a slope. This is the slope. So let me introduce a new symbol, mu P equal to RF plus, let me call this as SC times sigma P. What is SC? SC is the slope. Why did I take C? Because this has parameters related to the C, mu C and sigma C, correct? So this is my slope. So here is the thing. Whatever C you choose, correct? C can be anywhere on the hyperbola. C can be anywhere on the hyperbola. The resulting portfolio will have a risk return equation, something like this. RF you cannot change. It's the return of the risk-free asset that is given. What you can choose is C, which is the risky portfolio that I want to combine with risk-free asset, correct? Depending on which C you choose, you get the corresponding slope. So mu of the portfolio increases with risk through this slope. Okay, so you can define this as, rate of change of return with respect to risk, or what is the additional mean return you generate for taking 1 unit of additional risk. That is this SC. Okay, this is called the sharp ratio of portfolio C. For any portfolio, you take the mean return of that portfolio minus risk-free asset by sigma of that portfolio. That's the Sharpe ratio of the portfolio. Here, SC means it's the Sharpe ratio of C. But C can be anything on the hyperbola, right? So which C gives you the most bang for your buck, or the most efficient increase in your return for each additional unit of risk that you take? Which portfolio or C gives you the highest increase in return? That's the tangency portfolio. Okay, so let me call this portfolio as T. Let's call this portfolio as T. That's the tangency portfolio. Okay, so you can clearly see in the picture, this is the line with the highest slope. Can you get a better slope than this? Take C anywhere. It will be a line joining this point and the C. The highest possible slope that you can get is if you take the tangency portfolio. You cannot get higher than this. If you take higher than this, it will escape the hyperbola, which is not a possible portfolio. Right? The tangency portfolio is the one with the highest slope, is the one with the highest Sharpe ratio, because Sharpe ratio is the slope. Correct? And that's why it is part of the efficient frontier. So everything falls in place. Please remember, the slope of the return and risk profile dictates what is the rate of rise in mean return when you take 1 additional unit of risk. Higher the slope, more efficient is the portfolio. Correct? The highest possible slope geometrically is clearly the one with the tangency portfolio, right? So of all the portfolios on the hyperbola, you should choose the tangency portfolio to mix with the risk-free asset, and that gives you the efficient frontier. And tangency portfolio is the one with the highest Sharpe ratio, which is clearly geometrically, you can see that that's the one with the highest slope, right? So tangency portfolio is the one with highest Sharpe ratio. Sharpe ratio for that would be ST, which is mu T minus RF by sigma T. Remember, every point in the hyperbola has a different Sharpe ratio. It depends on the particular portfolio's mean and the sigma, and then that's the Sharpe ratio. And this is the slope that enters into this equation. Okay, and this is the highest possible slope or the highest possible Sharpe ratio. Question from Bassist. So we use solver to get highest Sharpe ratio. You can do that. Yes. So we'll do that exercise another time. But intuitively, I think everything falls in place. It's not rocket science. Things get a lot philosophical when we talk about equilibrium and why tangency portfolio should be the market portfolio and things like that. We'll discuss next time. Yeah, so by the way, we already discussed all of these. Yeah, so the highest possible slope is the one with the tangency portfolio. That's the one with the highest Sharpe ratio. And this line is called as CML, capital market line. Okay. In general, when you connect the risk-free asset to any portfolio, you get a line that is called as capital allocation line, CAL. But if you take the tangency portfolio, it's a special case. Then the line that you get is called CML, capital market line. Okay. This tangency portfolio is actually the market portfolio in the sense that all the assets that you see in the market are invested based on the weights are the market capitalization. That becomes a little philosophical. We'll talk about that later. And this is all that we talked about. Tangency portfolio, Sharpe ratio of the tangency portfolio is given by this. This is in general, if you choose C, this is the Sharpe ratio for the portfolio C. That's the slope. And the best slope is when you take the tangency portfolio. Yeah, I guess that's all I had. Yeah, any questions before we wrap up? I don't have anything else for today. I'm good. Did you follow through the flow of these concepts and maths? I tried to keep it as simple as possible, but the maths is not difficult at all when it comes to portfolio management. At least we're talking about 1952 infrastructure, which was what, 70 years ago? But there has been a lot of advancements uh, in the late years with respect to dynamic programming, stochastic control, machine learning, uh, all kinds of things people are doing in portfolio management these days. Okay, all right. I will announce when we'll have. So uh, tomorrow we'll have a class, but I'll announce more to come in the group. So check the group. Okay, thank you so much for your time, guys. See you tomorrow.